Hello, everybody, and welcome to my first calculus lesson. And this is my first video in the series. Now, for this, and sorry for the lack of pretty good setup. I'm just kind of doing it on my desktop. I'm using this textbook for the reference, so if you want to check that out. I believe a lot of high school students use this for AP tests and all that, but the material should be the same. And the goal of this series is to explain sort of the fundamental ideas of calculus, because a lot of people, don't really understand what calculus is. So let me describe what a calculus is. Now, there are two parts to calculus. One part being the derivatives, and the other part being integrals. Now, this is only speaking for calculus 1 right now. And so, calculus 2, calculus 3, those are a little bit different, but for now, we're only going to talk in calculus 1. And so, let's say, and derivative, right? We're going to talk about derivatives today. And maybe next time, if we don't finish today. So, derivative is usually written, let's see if you guys can see this. Okay, derivative is usually written in dx or dy dx, whatever. The main thing is the d just represents a change, and derivative, you can think of it as change or the rate of change, but it's a change. And so the way we read dy dx is, we just like to call it dy dx, but you can think of it as the change of y in terms of x. And so let me explain to you what change of y in terms of x sort of means, right? And so imagine, now this is very crude setup, but I'm trying to do my best. Now imagine a function. Let's say like this. And I forgot to mention this, but change is also, you can express it as a slope. So for example, we're familiar with this, with the standard, I guess, notation for a function. For example, y equals 2x, right? And here, this 2 represents the slope, right? So if we imagine y equals 2x, and you guys should probably already know what this looks like. It's just a line, and if you do, right, this is all algebra stuff, y2 minus y1 over x2 minus x1, that gives you the slope, right? It's the rate of change of y as the graph moves along the x-axis. That's what it means by change of y in terms of x, so, or dy dx. Now we can look at another function like this, and this is, let's say this is f of x is x squared. Can you guys still see this? Okay. Now this is a curved function, right? It's not a straight line like this one. And so we can approximate a slope. Let's say this is 1 1, and this is let's say 3 9. So we'll sort of have a function like this. And if we want to find a slope of this, a rough estimate of the slope, it's gonna be, so we're gonna draw a line like this, and it's gonna be 9 minus 1 over 3 minus 1, which gives us 8 over 2, which is 4. Now, in physics, this dy dx is also known as the instantaneous rate of change. Now, what does instantaneous mean? Instantaneous just means like happening at that moment. And so if you imagine like a car driving and you put you hit the gas pedal and it starts accelerating, it's not gonna go in a constant speed. It's gonna gradually increase the speed, right? And so how fast is the speed changing at that exact moment when you look at the speedometer? That's what it means. And so you can also find acceleration, right? Acceleration is a rate of change of speed, basically. And so if you take a derivative of a position function, you can find the rate of change in terms of x, or in terms of time, I guess, if you want to do physics. But that's for the later topic. And right now we want to focus on derivatives only. Now imagine, what if I brought this a little bit closer, right? And this is a slope from 1 to 3 seconds. We're gonna call this time, right? Because time is easy to imagine, right? 1 to 3 seconds is 4. Now, what if we want to find, this is 2 and 4, a slope that goes like this? Now, if you notice, it's a little bit less steep, so we're expecting a number that's less than 4. So let's figure out what the slope is going to be. So it's going to be 4 minus 1 over 2 minus 1 is 3. Now, how do we get to instantaneous? Well, instantaneous means the moment you look at your speedometer, pretty much. And so this time has to be so short that it's basically like 0, right? The difference in time, in other words, the delta x, right? You can kind of imagine this as a delta, is delta y over delta x. This is a pretty good way to imagine that. The time in between, the time that it takes to, I guess, move to the next position has to be like almost 0. And so this line is gradually going to move like this until, if we zoom in, now this is it's a zoomed in version. Here is our original point, 1, 1. We started at 3.9, and our time is getting shorter and shorter until they get so close so that basically this is like 1.0, 0.0000000000001, and then some y value, right? So how can we express this in a mathematical term? Well, this is where limit comes in. Now, limit is very interesting, and in calculus 2, I think, we go a little bit more in depth with limits. But limit is simply expressed like this. Lim, right? Pretty simple enough. And let me draw the graph as a reference again. Now we said that the distance between the x's, right, we can call it delta x, right? It's the difference between x2 minus x1, right? Now as this gets closer and closer together, as delta x gets closer and closer together, we're approaching instantaneous rate of change, or instantaneous slope, is, if you want to think about it that way. And so we can just write it over here. Simply just copy this down as, so we read it as limit as delta x approaches, right? This delta x gets closer and closer. So what is going to approach? It's going to approach 0. It's not going to get to 0, but it'll be incredibly close to 0. As that happens, and we said this function is x squared. As this happens, what happens to the slope of this function? That's what it's really asking. Now, I didn't really cover, evaluating limits and all that. Those stuff are, I think, pretty easy if you just know what this means, and you can just, follow the rules, I guess. There are some rules you must learn, but I'm not going to cover that in this video. I'm going to basically define derivative. So that's how we express derivative, and we can also write it dy dx. These are the same thing, right? So what happens? What happens? So as our dx approaches infinitely close, we started with this line that, there's some gap in between, right? But if this gets so close, this line that forms or that represents a slope is going to be tangential to the original function. Tangential meaning they're like kind of skimming the surface. And so if we imagine a tangential line, let's say right here at 1.1 or 1.1, what is, it's gonna be like this. Right? As delta x approaches 0. That's what it's doing. And so this gives you the instantaneous rate of change by using the definition of what do you call it? Of limit. And if you look in the textbook, is this still recording? Okay, good. Let's see where it talks about. Okay, so limits and properties. Infinite limits, the derivative and tangent line problems. Okay, so we're gonna go to 116. Oh, I think I went past. Okay, so here it talks about limits. Let's see, limits define derivative, so you must learn it. Here it is. So as this delta x approaches 0, what's going to happen? The line that represents the slope, here it describes it very well. It's going to be a tangent line. And I'm trying to find the definition of a derivative. There we go. The definition of a derivative. So let me write this down so you can see it better. So dy dx, or the instantaneous rate of change of y in terms of x, is defined by now. What does this mean? What does that mean? So let me explain to you what that means using the same graph. So imagine we have a point, and this is similar to, right? This is a very similar form of y2 minus y1, x1 minus x2. Now this delta x, right? That's basically delta x. Now, and this, I guess you can call it y1, this y2. And so if this becomes really, really close to 0, it's basically gonna be f of x, I guess f of x2 minus f of x1, right? And so this is a definition of a derivative, like I said, and it's basically deriving, right? Describing x plus some delta x. Let's say this is some delta x right here. As this approaches 0, in other words, this gap between the 2 points approach 0, what is the slope, right? This is a slope. What is right? Or what is the change of y, I guess, over change of x? And so I'm trying to find, okay. And so there are many rules that apply to derivatives, but a very first thing I guess you learn is the I think it's called the power rule. And so we had a function like this, and it looks like this. And well, let's say this is, we're gonna choose a different point, 2 and 4. And an example would be find the, sorry for the poor handwriting, derivative at x equals 2, right? So in other words, when you read this, you should be thinking like this. Okay, find the derivative. So what is the slope of a tangent line that goes through 2.4? I mean 2 and 4, right? And so this power rule, I'm going to rewrite the function right here. Basically, if you have right, if you want to take it, this means take a derivative of this function. So if you want to take a derivative of this function, you simply subtract 1 from the exponent, and then you multiply it by the original exponent. And this comes from the definition of the derivative, which I described right here. This is also called the difference quotient. You should already know what a difference quotient is and how to do it from pre-calculus, and maybe algebra if you this is like pre-calculus stuff. And so you evaluate the limits, and you end up with a pattern, right? And basically every pattern you evaluate it ends up like this. So this is like a shortcut. You don't have to, because if you did the difference quotient before, it's very, very cumbersome. It's a lot of just writing, and you lose track. But this is a shortcut. So let's apply the same thing here. So dy dx of this function is now this also means, or you can rewrite this as a f prime of x. This little thing, apostrophe, I guess, represents that it is a first. Now there's one apostrophe, so it represents the first derivative of f of x, right? That's what we're doing here. So we subtract the 1 from the 2, so it's going to be x to the 1 power. We don't have to write the 1 because it's, okay, I'll just write it, right? And then we subtract 1, okay, we did that, and then we multiply the x by the original power, and we end up with 2x. So therefore, oh no, not yet. dy dx, or the derivative of a function x squared, is 2x. Now simply, just we just substitute in 2, and so this goes here, and like I said, right, this is the same thing, right? I'm just rewriting what I wrote. And you can also write this as f prime of 2, because now we're going to be substituting 2 for this function that we got as a result of taking the derivative of this x squared function, is equal to 2, and this 2 goes right here, times 2 is 4. And so let's go ahead and verify that here, that the slope is actually 4. And so we're gonna choose 2 points. So point 1 is gonna be 2 and 4, and because the delta x, or the difference in x, is approaching 0, we're gonna choose a point that's very, very close to 2. Right, so a very close point, I guess, would be, let's say, like 2.0001. Right, that's a very, very small change in x, almost 0, but not yet. Now, as this change, right, becomes 0, basically we're doing the derivative, but I can't write infinitely many zeros, so I'm just gonna end up with 3 zeros, right? And if we evaluate that, actually, let me. Oh, I don't have a calculator with me, but I guess you can write this. Squared, and hold on, let me find the calculator and give you the exact numbers. Alright, I'm back with the calculator. So 2.0001 squared is actually 4.0004 and then 0001. That's super tiny. I don't have room for this. So let's find the slope. Y2 minus the y1. This is the same thing. Okay. So y2 minus the y1 over x2 minus the x1. Like this. And what is that? Let me quickly do that on the calculator, and I'll just use the exact number. Let's see if this can focus. Okay, there we go. So this minus 4 over the delta x, which is 2.0001 minus 2. And it should be a number very, very close to 4. Yep, 4.0001. Let's get it refocused. Is it focusing? Okay. Now, we can imagine, right, if these two x values were a lot closer, we get a number that's so close to 4 that is basically 4. And that's what we did here. As the distance between the x's decrease, what happens to the slope of this tangent line? And so now that we found the slope, let's actually go ahead and find a line, the equation of a line that goes through that point. And so in the beginning, we defined dy dx as a slope, right? And we already found it. F prime of 2 is 4, which is also the slope of a line, of the tangent line, right? And our original point was 2, 4. And so let's just use the standard point slope form, because that's the easiest one. So the point slope form is y, y minus y1 is equal to the slope, we'll just write it as m, x minus x1. Now this, again, is the slope. And so we just substitute in the points. It goes y minus 4 is equal to the slope that we found, 4 times x minus the 2 from the original point. And you can leave it as that. That is the equation of a tangent line of f of x equals x squared, which goes through the point 2, 4. And so, if you want to clean this up and write this more neatly, I guess it would be y equals, if this is the kind of the standard form that you're used to seeing, minus 8 plus 4, so y is equal to 4x minus 4. Now notice that we still have the slope of 4, and so I'm going to show you what that looks like on a calculator. So let's see if this can focus. Now if our math is correct, we should see the original function of f of x is equal to x squared, and then this new one that we found, let's see, 4x minus 4. Now when we graph this, we're going to see this original function as this sort of curved line, and then the second equation should be tangential to that function at 2 and 4, this original point that we found. So let's go ahead and graph that. And well, it's not exactly tangential. It's kind of hard to see it there, but that's the idea. You're gonna have to form a tangent point. Now, if you actually zoom in, I will try to zoom in. So I guess we can zoom in on this x equals 2 and y equals 4 almost, right? You can see this function is barely touching that point. It's actually going through, and it's barely skimming. And that's what it means by instantaneous rate of change. Now, an application to this would be, and there are many different rules you must learn when you're doing derivative calculus. They're all defined here. So the ones you see with d over dx or d dx are all the different derivative rules you must learn. It's basic differential rules, and we're going to talk about the integral rules later, so don't worry about it right now. And these are just, you have to memorize them. There's no other way around it, but the idea works the same. Derivative gives you the instantaneous rate of change. And so if we imagine, and this is very, very, very related to physics, and so I don't want to write the whole thing down because it's going to be a long question, but I'll just say it here. So imagine a particle. No, not even particle. Imagine a car, right? A car moving, and its position is given by, let's see, position in terms of time is given by x cubed minus 3x minus 2. And it wants you to find So I want you to find the speed after 5 seconds. Now previously, if you have no knowledge of calculus, you wouldn't be able to do this because, like, what are you going to do with it, right? But now you know calculus. So speed is position over time. Now this can be acquired by taking the derivative of the speed function, because now we're saying that the rate of change of your position in terms of time. So that's what it means by speed. That's what it is, right? Speed is a change in position, I guess, over change in time, or rewrite this as change in distance in time. Now, you can argue that whatever, it has to be like this displacement, whatever. We're only gonna worry about distance because we're covering the ideas of calculus. And so we'll do d of dx. Now instead of writing the y here, I'm gonna write the y here, and this y is that s of t, right? So derivative of x cubed minus 3x minus 2. Now I guess I should mention that this should really be, I'll rewrite this. This should really be in terms of time, because now we're dealing with time here. But this can be any variable. This can usually it's x or t, and so on and so forth. Now if you apply the power rule, it's gonna be, so that turns into 3x squared because we multiply by this power and we subtract 1. And this right here is 3x to the first power. I'm sorry about that, guys. My camera died in the middle. So let's continue. This to the x, this is x to the first power. Okay, good. And when I subtract 1 by this constant 3, I end up with, well, negative 3, I guess. Negative 3. And this basically becomes 1 minus 1. So this turns into x to the 0 power. And x, anything to the 0 power is 1. So if you notice, any constant times an x, and if you take a derivative of that, you just leave with this constant right here. And derivative of a 2, now 2 is a constant, and there is a rule that if you take a derivative of a constant, that is 0. And it makes sense because let's say I have a function like this, y is equal to 2, that's what it means, right? And derivative is a slope. So what is the slope of this function? Well, these two y are same, and so the slope is 0. 0. So minus 0. So let me rewrite this so it looks a little bit clear. Now I'm going to rewrite this as a f prime of x. Sorry about that, my phone died again. Okay. And okay, so that's our derivative function. Now this gives us the instantaneous rate of change at any time. We just gotta substitute it in any seconds. Now this question asks for the speed after 5 seconds. And so we're gonna write f prime of 5 is 3 to the 3 times 5 squared minus 3, which is 3 times 25 minus 3, and I believe this is 75 minus 3, and 72. Now I didn't specify the units. I would assume that the speed, well, we know the time. Let's just say we just did it in miles, right? Sorry, meters. Usually it's in meters. So meters per second. And our unit concurs with our notational derivative. this is dt. This is change in time, and this is change in position, and meters is a unit of position. Seconds is a unit of time. And so that's one way you can use derivative. Now, if you're driving a car, your car's like doing this all by itself with a computer. Okay. And there are many uses of derivatives. For example, one of my favorite is the optimization of areas. Let's see where optimization is in this book. So optimization. So we already covered limits. We already covered differentiation. Now I didn't cover like all the rules. You just have to memorize them. Okay, so application of differentiation. So extrema on an interval. Optimization is applying the idea of extrema, and when derivative is 0 and all that. And let's see. Rolle's theorem, concavity. There we go, optimization problems. So a question in an optimization problem would ask you, for example, if you're building a fence around your backyard, and let's say you only have like 100 meters of material of fencing. So what is the length and the width so that you can maximize the area or optimize the area, right? And that's what it is. That's very useful in construction, artwork, maybe if you're building like a business. So maximum volume, all same idea. And yeah, like I said, construction, very useful. And what else? I'm trying to think. I guess in like advanced physics, you would use derivatives. I guess like a fastest route from point A to B, with obstacles, and like for example, if you're going on a straight on a nice paved road, you can go faster, but that might be longer in distance. So what is the fastest way you can get from point A to point B with all the obstacles in mind? Trying to think what else. Yeah, well, it's derivative is very useful in business as well, and creating business models and stuff. And so there's a lot of use for derivatives. And let's see what we can do with derivatives. So I guess it kind of okay. So extrema, you can see where like when something has reached its max, like when something stops growing and starts to decay, you can know when that happens. And I also I think there's a law somewhere in the United States that if you, for example, if the speed limit is like 60 miles an hour, and you get caught with a speeding ticket, and the police can actually use calculus and derivative to prove that from the time that you I guess started driving to the time you got caught speeding, they can actually prove that you did indeed go over speed. And a lot of uses of calculus, just derivatives. Now integral I think has more uses, but that is the basic idea of calculus. I mean derivative calculus at least. And so let's recap what we learned. this what we're doing? Okay. So derivative is just a slope, and it's change in y over change in x. And basically, if you have a function and you want to find the instantaneous rate of change of y as a function of x, right, in terms of x, what is the instantaneous rate of change? And so the way you do that is you bring the x's closer and closer and closer together so that they eventually become so close together that it's basically zero. And you can express that using a limit. So as the change of x, the difference in x becomes zero, what is a slope, I guess, and that is a definition of derivative. I guess I kind of wrote all over it, but hopefully it made sense while I did write all over it. And that's basically what it's going to look like when the delta x becomes so close together that it's basically zero, right? This is what is happening right now. You know, limit as delta x approaches zero, so this gets closer and closer. And then we looked at some. Oh, we did this one, and we looked at some examples. And probably the most important rule, the derivative rule, which is the power rule, how to use them, and different notations of derivative. We haven't covered second derivative yet, and I think I might do that in the next video. But yeah, how to read these notations, and we did an example, and we did in fact verify that the slope was 4, as these 2 points were incredibly close. And we learned how to we learned how to write the function that goes through a certain point and is also tangential to the original function that we were given right here, or right there. And then equation of a tangent line of f(x) is equal to x squared, which goes through the point 2, 4. And we also did sort of like a physics problem. If you were given a position function, find the speed after x amount of seconds. And so this basically just means the difference between the distance and difference between the time, over the difference of time. And we also covered that if you take a derivative of a constant, that the slope is 0, so you can just write 0 over there. And we applied the power rule there. And then you just gotta substitute in 5 for time, because this gives you the function of speed. This gives you the function of speed. And yeah, you can just find the slope. Find the speed at any time with this function of this specific car. And we found out that it's 72 meters per second. That is incredibly fast, by the way. You would not survive that. Yeah, maybe you would. No, this is way too fast. Probably too fast to drive in a street, anyways. Let's see. And we talked about how calculus is useful in real life. Let's see. Calculus. There was one more thing I wanted to cover. I forgot what it was. So, I remember what I was going to talk about, but I'll save that for next time. Next time we're going to be covering how to graph derivatives. It's going to be very interesting, and stay tuned for the next video. And after that, I'll probably, I don't know yet, but I might do some more examples or go into integral, basic idea of integral. But we'll see. But definitely next time I'm going to be covering graphing derivatives. And yeah, well, thanks for watching, guys. Stay tuned. And also leave a like, because I'm doing this for free. And yeah, leave a like. That really means a lot to me. And please also leave a comment of what you thought of this lesson. I'm pretty young, but so far calculus has been like my favorite class. So I'll be doing more videos, and if you want to get more videos from me, just go ahead and subscribe. And yeah, like I said, stay tuned. I'll see you guys in the next video.